All right, so I probably don't have to introduce Radley Horton again. You heard from him this morning about climate change, but he's going to talk to us now about threats to North American forests from the southern pine beetle headed northward.
Thanks. Okay, yeah, so this is a study that I guess was recently accepted to Nature Climate Change. We may be doing sort of a last stage of revisions to it, but hopefully this will be out in the next couple months or so. Study led by Corey Less, who's going to be a student of mine at Columbia next year, with a lot of participation from folks in the Northeast Climate Science Center. Ethan Kofel has been a fellow for the Climate Science Center. Tony D'Amato has been a consortium lead, and we also had great participation from agencies, including Kevin Dodds, senior from USDA Forest Service. Okay, so I'll talk about the motivation and objectives of our study, looking at the southern pine beetle. Have time to do some overview of the methods, get into the main results of the study, and talk about some of the impacts, implications of the work, also some of the limitations, of which there are many that we can talk a little bit about. But I think it's hopefully useful as sort of a first brush, or sort of early look at how changes in extreme temperature could impact that species, and maybe some motivations for similar future studies. So the primary motivation for the study comes from the realization that much of the impact of climate change will be felt through changing extremes, something that I highlighted earlier. And most, but not all, climate projections suggest that at the cold end of the distribution, we may actually see that sort of coldest day per year warming more than the average temperature in winter, say, in some regions. So that was one of our motivations, the sort of strong expectation that there's going to be less extreme cold temperatures, and potentially that those coldest days of the year will be a lot warmer than they were in the past. We realize that ecosystem responses are highly complex, not can be highly complex. What we didn't do in this study, we didn't have the expertise to do a sort of computationally comprehensive process-based modeling study. So I'll describe how we just looked at a historical relationship in distribution of southern pine beetle and temperature, and then also some findings from lab-based studies of what critical temperatures the species can survive. And then basically just looked at the temperature projections, what that would imply. So I guess the sort of broader motivation is this question of to what extent are thresholds relevant. I feel like as a climate scientist who doesn't fully understand ecosystems or societal impacts, it's very appealing to try to identify threshold temperatures, for example, knowing that a specific temperature is never going to be able to describe all of the impacts, but can they still be relevant? Can there be sort of specific threshold temperature, for example, that have a relatively large impact on a species? Because to the extent that that's true, it enables us to, without considering all the complexities, point to potentially large shifts in climate that could change these distributions a lot. Okay, so let's delve into the specifics now. Southern pine beetle. This is already a major forest pest in the southeast U.S. among the many beetle species, a couple of which have already been mentioned. Is responsible for something like 1.7 billion in timber losses specifically over a relatively recent 15-year period. And there's a lot of evidence that it's been spreading north, as a lot of you may know better than I. Certainly across New Jersey, you started seeing it earlier this century. But then these sightings in Long Island, 2014, Connecticut and Massachusetts, 2015, quite possibly others that I don't know about that some of you may even since that time. Maybe a little bit of this is people looking more closely for it. Probably that is part of it, but I don't think anyone thinks that that's the whole story for why we're seeing it further north. And then the motivating question: will it continue to move north into more northern forests, and what would be the implications if it does? So this has gotten some coverage. A New York Times article a few years ago describing this phenomenon of the beetles making their way, really jumping a lot further north people expected. Okay, so what is this relationship between the southern pine beetle? Again, we kind of like went out and looked for species that we thought were societally important, that might have a relatively direct link to an extreme temperature threshold that could be easy to model. Southern pine beetle jumped out right away. There's papers, going back to the 1930s, looking at relationship between temperature and species distribution. Also, I said lab experiments, what temperatures actually kill the beetle, and most found somewhere between -14 and -20 Celsius would be lethal to a very high percentage or all of the beetles. So the basic sort of model for our study, you can see here the historical range of the southern pine beetle in the red since 2002, making its way into New Jersey, and then you can see those hash lines for sort of more recent locations. So the idea being, with the expectation that with climate change, warmer temperature, that threshold, that extreme cold temperature experienced, say, once per year, is going to make its way further to the north. Will the southern pine beetle move north with it? Okay, sort of unpack some of the observational data that we used to build our statistical model here. You can see a couple things. The gray area here, the black area is showing you back in 2002, sort of hectares killed by southern pine beetle. 2010, you're seeing a much larger area affected, including some movement to more central and even northern parts of New Jersey. We can also look at temperature records for 2 spots in New Jersey, Atlantic City here, Hightown there. This is for Hightown and Atlantic City. So what you're seeing here is the coldest temperature experienced during each of these years going back to 1960. And then what you're seeing here in the colors is a sort of plausible band for the minimum temperatures that are thought to be required to kill the species. So, for Atlantic City, you could make a case certainly that, over the last really 15 years, climate regime has emerged where your coldest temperature per year is not sufficient anymore to get that low. It doesn't mean you couldn't still have an individual year that goes significantly colder, but as I was saying earlier, the statistics have shifted. Likewise, for the spot further north in New Jersey, still occasionally some years dipping down, but again, lower frequency and less extreme magnitudes when it does happen. And there you can also see here the overall, very strong warming trend for each of those 2 places. Total area killed here, basically just the summing of those 2002 and 2010 across New Jersey. Okay, so our objective was to use that spatial relationship between southern pine beetle and cold extreme incidents to determine a range predicting temperature, and then to use climate model outputs to project the northward expansion under continued climate change. I think we understand the limitations of the study. I don't think that this, directly informs any decisions. That would probably be an overreach. But hopefully this kind of information could be useful in sort of encouraging further discussion. Discussion is probably already underway on some of these potential adaptation strategies, pros and cons of fire management, whatever it might be, or thinning of some of these stands, for example. And maybe also at least sort of opens up the thought in people's minds who live further north, managers further north, that even though this hasn't been seen yet, when you're considering future scenarios, it might be something to not rule out. So the structure of our model, what we do here, includes several components: forest surveys of southern pine beetle, observations of winter temperatures. We built a flow model based on sort of thickness of the trees, because we know that the beetles during the coldest time of winter tend to be burrowed away, seeking protection from that cold. So we have to model the fact that trees of different width are going to have a different amount of temperature buffering essentially on those coldest days. But based on the forest surveys, we can build that range predicting temperature. Then we go to the climate models, and the output that I'll show the most of is these maps of what we think the future range the southern pine beetle could be based on our assumptions here. So a little more on the sort of principle of overwintering, which is others have already talked to somewhat. But in the context of the southern pine beetle, like I said, that coldest temperature is most likely to occur when the beetle is overwintering. Woody tissue has a thermal inertia, which lessens the exposure of the southern pine beetle to that cold, right? A good evolutionary strategy. So there was a foam temperature model that was published about 10 years ago. Again, so that's the size essentially of the tree can tell you how much buffering that you get. Here's the model, pretty simple, sort of Newtonian heat flux model, or standard model, I'd say. And then you can just see a little bit of the results here. I'm sorry, I guess it's visible. Okay, so we just picked an individual month, January 1981, looked at daily temperatures across the month shown in red. That's the daily max. Blue is the daily min. And then our modeled foam temperature here in the black. So sort of the key points to highlight is it doesn't get as cold inside the bark as you'd expect. There's also a little bit of a delay in terms of when it's experienced. But basically, you're getting a thermal buffer. We wanted to model that, included in the study. Okay, now let's look at individual grid boxes here within New Jersey to come up with sort of evidence for this range predicting temperature. So again, I apologize, it's a little hard to see. So basically what you're seeing here is across New Jersey, latitude on the y-axis, year on the x-axis. So each line is showing you a temperature contour. The blue is -14 Celsius. Green is -10 Celsius. So roughly 14 Fahrenheit there, roughly 21, excuse me, I got that wrong. Yeah, so the green is actually -9 Celsius. So something on the order of 16 Fahrenheit. Blue, -14 Celsius. So what's that? Yeah, 8 Fahrenheit, something like that. So basically what you're seeing is the furthest south latitude in a given year that you encountered that particular temperature threshold. So in the really cold years, that cold, extreme cold temperature, like 8 Fahrenheit, makes it all the way down, say, to 38 north or so. And then in the later years of the record, you're starting to pick up spotting indications of southern pine beetle presence. So the median latitude that southern pine beetle was observed in New Jersey in the black squares, and then the triangle showing the northernmost. So we're interested in that sort of, if there's a relationship there, basically, in recent years between those. Then in the bottom left, you have the sort of, if we average across, if we look at all these grid boxes within New Jersey and build sort of a distribution, the blue is showing you across that time period the sort of common minimum temperature occurrences. So, across a lot of these grid boxes, you'll have a coldest temperature in the year around -12 Celsius or so. But, for a smaller number of grid boxes, you get those outliers. And then the red is showing you the grid boxes that contain southern pine beetle, and the black is the total number of grid boxes. Okay, and then here, pointer's no longer working, but in the bottom right, basically just, we looked across several different temperatures to try to predict which temperature showed the strongest relationship between the latitude of northernmost cell that you found the southern pine beetle and the latitude of that corresponding temperature. And we actually found that the best relationship, let's stop working. Should I advance it here? Okay. Okay. Yeah, so again, if we look at that top figure, you can see the sort of long-term trend, which climate change presumably plays some role in, but also there's random variability from one year to the next. So as we're trying to build that perfect range predicting temperature, if you will, we know we're limited by a relatively small area, relatively small number of years as well, and a lot of other things going on, presumably besides climate, besides weather even. Autocorrelation, once a southern pine beetle is present in a grid box, that presumably increases, independent of temperature, the odds that it'll be there or nearby in the following year. And we're trying to tease out that long-term tendency, given these sort of different timescales of interaction. Okay, so yeah, so I mentioned earlier that we looked at the relationship across several different minimum temperature thresholds. We saw the best correlation for -10 Celsius, about 14 Fahrenheit, which is a little warmer, certainly, than what the lab experiments suggested. But the result's not dramatically different if you shift by a couple degrees in the year that you use. And then somewhat arbitrarily, when we went to what we defined as the year of emergence for the SPB suitable climate, we basically just said we're going to call that year of emergence the year when over the next 10 years, you never experience at that grid box a temperature that's colder than that threshold, in this case, -10 Celsius. Okay, there are residuals, certainly, there's always residuals. North and south of this climate-constrained range frontier. There's a lot of things to think about there, right? Some things to do with the host trees, things to do with forest conditions in that particular year, dynamics of predators and interaction with other species. Sort of operating on the assumption here that in terms of this long-term climate-driven trend, those other factors are less important. Okay, a little more on how we calculated this year of emergence. We're using daily temperature data from 27 different climate models, again, to capture the fact that climate models differ in the amount of warming they give with increasing greenhouse gases. They also differ in their regional responses, right? Some of the models, as you increase greenhouse gases, cause this part of the Northeast to warm more than others, for example, cause changes in drought as well that could be relevant. So what you're seeing here are, and then we also, as I said, modeled the phloem temperatures. And then for each grid box, we calculate a year of emergence for each climate model, for each assumption about future greenhouse gas concentrations. We use 2 of the RCPs, the assumptions of future greenhouse gas concentrations. Then we average the year of emergence across all those different model runs. Although I'll also show afterwards some analyses where we unpacked different sources of uncertainty, climate model uncertainty, greenhouse gas concentration uncertainty, phloem model uncertainty too. And there is a bias in these GCMs when we look at how they model daily temperature. Generally, the climate models have a little too thin a distribution. They don't give you enough really cold days. They don't give you enough really hot days. So we bias correct using observational data to account for that. Okay, so getting to some of the conclusions. Again, when we average across all those different climate models, all those different scenarios, what we see for the projected year of emergence by that definition I gave earlier is shown here. So you see by the 2020s, essentially, along a lot of the coastal domain, all the way, really far north into Nova Scotia. You could be in the SPB, Southern Pine Beetle suitable climate, moving to the northwest, essentially, and eventually more to the north, sets up the gradient, the delay. But even by say 2080, you can see large parts of Canada potentially vulnerable. And the actual temperature changes these correspond to, changes in that coldest temperature per year, range from about 3 to 7 degrees Celsius. So you see, really huge changes. And then, of course, as you can see, we've also overlaid different forest types here. For the purposes of this study, we assume that the forest distribution doesn't change at all. We've already talked a little bit about follow-up work that might question that assumption. But again, as I said earlier, we wanted to start with just sort of the simple relationship between the temperature and SPB. Then in future work, working with people with a lot more expertise and process modelers, unpack additional factors that could impact these results. Okay, and just sort of putting all that together, these results suggest that by 2050, 78% of pitch pine area could be affected. And by 2080, 71% of red pine, 48% of jack pine potentially. And as we'll see a little later, we don't mean to suggest here that for sure southern pine beetle, will be successful in these tree species. I think that very much remains to be seen. But again, we're trying to highlight potential risk. So as I said, there's a lot of uncertainty, as always in these types of projections. We can unpack a few of those uncertainty types here. Let's look at how much can be explained across the climate models, across the emission scenarios, and across internal variability, for example. So going back to all the components of the model, some of the uncertainties I'll briefly touch upon here are the phloem simulation, the different climate models, and the emissions scenarios, and a little bit of the uncertainty that's just due to that unpredictable internal variability. So that bar on the left is essentially showing you how much of the uncertainty in the year of emergence can be attributed to each of those factors that I just mentioned. So I said that I'd averaged a bunch of simulations, so it's 162 different simulations. That's what you get if you take the 27 climate models multiplied by 3 different K values, essentially based on the size of the tree. That's the bark thermal buffering, that K value, and then the 2 representative concentration pathways. That gets you to 162. We also, in a side analysis, for a few climate models where there were many different simulations, or basically they were run with different start date initial conditions, we looked at which of those start dates you used to run the model could impact the results. And we found that could be account for about 13% of the range of results, the variance, if you will, in the final year of emergence could be due to what's considered totally unpredictable, basically the internal conditions, the fact that one year the ocean can be a little warmer, essentially butterfly effect that can get you on a trajectory. We'll never reduce that 13%, we think. But arguably, I think more importantly, given the consequence, up to 83% is effectively irreducible. What we mean by that is that, in the near term, at least, the representation concentration pathways, whether we're on that RCP 4.5 world where we pretty dramatically and soon as a society reduce our emissions, or whether we stay on the trajectory of rapid, continued increases or continuation of high greenhouse gas emissions for the next few decades, that decision doesn't impact these results at all. It does as you get further out in the century, but we're really sort of locked in over the next couple decades to further warming that's going to cause that year of emergence to move. And then also within the climate modeling side of it, the 27 different global climate models, fact of the matter is we're not in the next few years and in the next 10 years going to be able to say which of those climate models was right. That's a longer process. So really just the overall point to highlight here is that these uncertainties aren't going away, which probably isn't really much of a surprise. We basically have to accept that there's a range of possible outcomes here. And as I said, just sort of identified what has the potential to be a very large change. I think future work can try to reduce some of these uncertainties, but on the climate side, I think these uncertainties aren't likely to narrow a lot in terms of the climate component to it. So what are the potential impacts, implications of the results? Certainly disruption of local ecosystem services if these trees are dying off. Obviously, all the biogeochemical, hydrological regulation that these tree species provide. Probably lots of threats to the native biodiversity. Others here could tell a lot more about that, including some iconic and endangered species and communities. Shifts in forest structure we could also imagine as a result of the southern pine beetle effects, transient mortality, and maybe longer term changes in biodiversity, tree diversity. Lost income from forestry and tourism, and potentially as you get sort of further out into the century, if some of the more ominous projections for late century, the species moving far into Canada, that would certainly have implications on global carbon regulation. And we weren't even thinking there specifically about fire risk necessarily, although that would certainly be part of it. Limitations and caveats of the work, there are plenty. It is still relatively, I'd say, it's uncertain whether southern pine beetle will thrive in those northern pine forests. It is important to remember, though, that the species has shown ability to survive in many different trees. and there's evidence of it affecting new northern pine species. So there's certainly at least cause for concern. Our model didn't try at all to look at population dynamics. In the real world, there's a difference between, identifying the southern pine beetle, in a field survey and actually being established there. We didn't really look at that. How will predation change? How will life cycle and phenology change due to other factors? We didn't really look at that. I think it's actually an open question how drought could impact the species. Just from some of the comments we got back from reviewers, there's a case that there may be high drought sensitivity, and there's a case that there may not. But certainly we can all agree that we need to look at things other than just that extreme minimum temperature on the climate side. And the other thing I sort of alluded to in my earlier talk was these model projections of what could happen to extreme coldest temperatures may not be quite right. We could imagine situations where if the jet stream does shift with changes in Arctic sea ice, we could see shifts in prolonged cold air outbreaks that could make these results less extreme, more extreme. We could also imagine snow cover feedbacks in some of these areas if you're going to reduce duration of the winter season where you have snow cover. We could probably pretty much assume that would have a pretty direct effect on how cold it's getting at night in some of these places. And we weren't really able to model that except insofar as climate models can capture appropriate levels of snow cover in these ecosystems, which is certainly debatable. And there's no way they can do it at the sort of fine scale of the actual environments, mountains and things like that. But even with all those caveats, clearly I think this species poses a threat to the forests of eastern North America in the coming decades. The sort of assumption I think should be that there are a lot of potential undesirable impacts. Burden of proof I think is to show that wouldn't be the case, although it's certainly possible. And it's also important to keep in mind that there are management options, management strategies that have been used in more southern parts of the U.S. that should be kept in mind too. We don't have to sort of take these results as a given. Here's some of the references that I talked about. So I'll leave it there.